Welcome to physics class. Good morning everyone. My name is Gias Uddin. My dear students, today we are going to discuss about some important numerical based on Broglie hypothesis. Numerical problem based on Broglie hypothesis. So our first numerical, the statement of this numerical problem: an electron microscope uses electrons accelerated by a voltage of 50 kilo electron volt. Determine the Broglie wavelength associated with the electrons if other factors such as numerical aperture etc. are taken to be roughly the same. How does the resolving power of an electron microscope compare with that of an optical microscope, given that wavelength of optical microscope is 6000 angstrom? Okay, so the given information of this question, first of all we are going to find out the wavelength of a electron microscope. Okay, solution. Given energy is 50 kilo electron volt, so we can write E equal 50 kilo electron volt. We know that 1 kilo, it means that 10 cube into 10 cube, and 1 electron volt equal 1.6 into 10 to the minus 19 joule, and this is equal to 80 into 10 to the power minus 16 joule. 80 into 10 to the power minus 16 joule. Again, mass of particle is electron, so mass of electron equal 9.1 into 10 to the power minus 31 kg, and charge of electron equal 1.6 into 10 to the power minus 19 coulomb, and also Planck constant H equal 6.62 into 10 to the power minus 34 joule second. Okay, 34 joule second. Now we are going to find out lambda equal what? So we know that first of all we are going to find out wavelength of electron. So lambda equal H by under root of 2me. Okay. Now lambda equal, the value of H equal 6.62 into 10 to the power minus 34, and 2 into the value of m equal 9.1 into 10 to the power minus 31 into energy, this is equal to 80 into 10 to the power 16. 80 into 10 to the power minus 16. After solving this part, you will get the result is 5.49 into 10 to the power minus 12 meter. So this is our required wavelength associated with electron. Okay, now we are going to find out resolving power. Again we know that resolving power is inversely proportional to wavelength. Resolving power is inversely proportional to 1 by lambda. So we can say that resolving power of electron microscope divided by resolving power of optical microscope is equal to lambda wavelength of optical microscope divided by wavelength of electron microscope. Now we can put the value lambda optical wavelength of optical microscope, this is equal to 600 angstrom. So we can write the value of lambda O equal 600 angstrom, and lambda E equal, this is 5.49 into 10 to the power minus 12, and angstrom is not SI unit of the wavelength, so it should be converted in SI system. So we can write 6000 into 1 angstrom, that means 10 to the minus 10 meter, divided by 5.49 into 10 to the minus 12. After solving this part, we will get result equal 1.09 into 10 to the power 5. Okay, so this is our required comparison between resolving power of electron microscope and resolving power of optical microscope. For your better understanding, I am going to repeat this once again. The statement of this question: an electron microscope uses electron accelerated by a voltage of 50 kilo electron volt. Determine the de Broglie wavelength associated with the electrons. If other factors such as numerical aperture etc. are taken to be roughly the same, how does the resolving power of an electron microscope compare with that of an optical microscope, given that wavelength of the optical microscope is 6000 angstrom? So the given information of this question, first of all we are going to find out the wavelength associated with electron. So the energy is equal to 50 kilo electron volt. So 50 kilo electron volt, 50 kilo electron, kilo means 10 cube, okay? So 50 into 10 cube, and 1 electron volt is equal to 1.6 into 10 to the minus 19 joule. So finally we can write 80 into 10 to the minus 16 joule, and mass of the electron equal 9.1 into 10 to the minus 31 kg, and Q, this is the charge of the electron, so 1.6 into 10 to the minus 19 coulomb, and H is Planck constant, this is equal to 6.62 into 10 to the minus 34 joule second, and lambda equal what? We know that lambda equal h by under root of 2 me. This is the expression of de Broglie wavelength in terms of energy. So we can write lambda equal h by under root of 2 me. When all the values substituted in this equation, then we will get lambda e equal 5.49 into 10 to the minus 12 meter. Again we know that resolving power is inversely proportional to 1 by wavelength, that means 1 by lambda. So we can write resolving power of electron microscope divided by resolving power of optical microscope, and this is equal to wavelength of the optical microscope divided by wavelength of electron microscope. Now the value of the wavelength of optical microscope is already given in this question. So lambda O equal 6000 angstrom. So the value of lambda O equal 6000 angstrom, and divided by lambda E, the value of lambda E equal 5.49 into 10 to the minus 12 meter, and angstrom is not a SI unit of the wavelength, so it should be converted in SI system. So we can write 6000 into 10 to the minus 10, and after solving this part we will get 1.09 into 10 to the minus 5. So this is our required answer. Thank you. Okay, our next numerical problem is the statement of this problem: find the de Broglie wavelength of an electron in the third orbit of hydrogen atom. Okay, so the given information of this question, solution: particle is electron, this is clear that given mass of electron equal 9.1 into 10 to the power minus 31 kg, and Planck constant H equal 6.62 into 10 to the power minus 34 joule second. Okay, and charge of electron Q equal 1.6 into 10 to the power minus 19 coulomb. Okay, first of all we are going to find out energy associated with third orbit of Bohr. Okay, so we know that En equal minus 13.6 divided by n square electron volt. Okay, so n equal orbit number 3, so n equal 3, so we can write E3 equal minus, we can ignore, okay, so 13.6 divided by 3 square electron volt, and this is equal to 1.51 electron volt, and this is equal to 1.51, and we know that 1 electron volt equal 1.6 into 10 to the minus 19 joules. So this is the energy associated with third orbit of Bohr. Okay, now we are going to find out again lambda equal h by under root of 2 me, and this is de Broglie wavelength in terms of kinetic energy. Okay, so the value of h is Planck constant, so 6.62 into 10 to the power minus 34, and 2 into m is mass of electron, so this is equal to 9.1 into 10 to the power minus 31 into energy, this is equal to energy equal 1.51 into 1.6 into 10 to the minus 19. So we can write 1.5 into 1.6 1.51 into 1.6 into 10 to the power minus 19. After solving this part we will get the result is 10 to the power minus 9 meter, 10 to the minus 9 meter, and this is equal to 1 nanometer. Okay, because we know that 1 nanometer equal 10 to the minus 9 meter. For your better understanding, I am going to repeat it once again. The statement of this question: find the de Broglie wavelength of an electron in the third orbit of hydrogen atom. Okay, so the given information of this question, particle is electron, this is clear that, so we can write mass of electron particle 9.1 into 10 to the minus 31 kg, and charge of electron 1.6 into 10 to the minus 19 coulomb, and also Planck constant, this is equal to 6.62 into 10 to the minus 34 joule second, and n this is n equal 3. Okay, we know that energy associated with orbit number third orbit. Okay, so En equal minus 13.6 n square electron volt, and E3 equal 13.63 square into electron volt. Okay, and 1 electron volt equal 1.6 into 10 to the minus 19 joule. So finally we can write energy is equal to 1.51 into 1.6 into 10 to the minus 19 joule. Now we are going to find out lambda, that means wavelength associated with electron. Okay, so lambda equal h by under root of 2 me, and this is the expression of de Broglie wavelength in terms of energy. So we can write lambda equal h by under root of 2 me, and when the all values substituted in this equation, then we will then you will get 10 to the minus 9 meter, and we know that 10 to the minus 9 meter is equal to 1 nanometer, so we can write 1 nanometer. Thank you. Okay, our next numerical problem is the statement of this problem: what voltage must be applied to an electron microscope to produce electrons of 0.4 angstrom? Okay, so the solution of this question: particle is electron, so mass of electron equal 9.1 into 10 to the power minus 31 kg, and Planck constant H equals 6.62 into 10 to the power minus 34 joule second, and wavelength of electron 0.4 angstrom, and we know that angstrom is not SI unit of wavelength, so it should be converted in SI system. So we can write 0.4 into 10 to the power minus 10 meter, because we know that 1 angstrom equal 10 to the power minus 10 meter. Okay, and we are going to find out voltage equal what. Okay, so B equal what? We know that lambda equal h by under root of 2m qb. Q, this is equal to 1.6 into 10 to the power minus 19 coulomb. This is the charge value of the electron. Okay, after squaring both sides, we can write lambda square equal h square 2m q into b. Again we can write b equal h square divided by 2m q into lambda square. Okay, now b equal h by h square divided by 2m q into lambda square. The value of h equal 6.62 into 10 to the minus 34 joule second. So we can write 6.62 into 10 to the power minus 34, 2 into m, this is equal to mass of electron, so 9.1 into 10 to the minus 34, and charge value of electron 1.6 into 10 to the minus 19, and lambda this is equal to 0.4 into 10 to the minus 10 meter. Okay, so this is equal to 0.4 into 10 to the minus 10. After solving this part, we will get the result is 936.3 volt. So this is our required voltage. This is our required accelerating voltage. Okay, for your better understanding, I am going to repeat this once again. The statement of this question: what voltage must be applied to an electron microscope to produce electron of a 0.4 angstrom? From this question, the given data, mass of electron is 9.1 into 10 to the minus 31 kg, because particle is electron. This is already clear, electron, and Planck constant H equals 6.62 into 10 to the minus 34 joule second, and lambda 0.4 angstrom, and this is equal to 0.4 into 10 to the minus 10 meter, and this is Q, this is the charge value of the electron, this is equal to 1.6 into 10 to the minus 19 coulomb, and B equal what? We know that lambda equal h by under root of 2m qb. This is de Broglie wave equation in terms of the voltage. So after squaring both sides, we can write lambda square equal h square divided by 2m qb, and B equal h square divided by 2m q lambda square. Okay, when all values substituted in this equation, then we can after solving this part, we will get 936.3 volts. Thank you. Okay, this is our last numerical problem, and this is very simple, quite simple problem. So the statement of this question: calculate the de Broglie wavelength of 500 gram cricket ball which is flying within speed 13.9 meter per second. Very simple question. So solution: given mass of the ball is m equal 500 gram. As you know that gram is not SI unit of the mass, so it should be converted in SI system, and this is equal to 500 into 10 to the power minus 3 kg. Okay, so finally we can write 55 into 10 to the power minus 1 kg, and velocity of the mass equal velocity of the ball equal 13.9 meter per second. this is equal to 13.9 meter per second. Also Planck constant H equal 6.62 into 10 to the power minus 34 joule second, and lambda equal what? Okay, so we know that by using de Broglie wave equation, we know that lambda equal h by mb, okay. So lambda equal h by mb, the value of h equal 6.62 into 10 to the power minus 34, and m, this is equal to 5 into 10 to the power minus 1, 5 into 10 to the power minus 1, and velocity equal 13.9. After solving this part, we will get this is equal to 10 to the minus 24 angstrom. This is equal to 10 to the power minus 4 angstrom. Okay. Sorry, 10 to the power minus 24 angstrom. 24 angstrom. So this is our required wavelength associated with cricket ball. Thank you.